So we introduce a similarity transformation. Note that we are not trying to get analytical solution because it's a coupled equation. There is no clean way to solve it analytically. So what we are going to do is we are going to introduce similarity transformation. It just helps in solving the problem numerically and also to get the gradients in an easy fashion. Okay. So what we are going to do is we are going to introduce a similarity variable, which is y by x into the local Grashof number by 4 to the power of 1 by 4. Okay. So it's not a magic that these expressions have come through. People have actually done careful detailed analysis of the model equation and scaling in order to get these things. It's just out of the scope of this course, and we will not go into the details of how to get these similarities, but there is a formal method to do this. Okay. And then you define psi, which is essentially the stream function, the modified stream function. So now we rewrite all the model equations in terms of these similarity solution quantities. So you write u will be d psi by dy, which will be d psi by d eta into d eta by dy, and that will be 2 nu by x into Grashof number to the power of 1 by 2 into f prime of eta. So using these definitions, so we can rewrite the model equations as f triple prime plus 3f into f double prime plus 2f prime square plus t star equal to 0, and t star double prime plus 3 times Prandtl number into f into t star prime equal to 0. And the boundary conditions would be when eta is 0, f equal to f prime equal to 0 and t star equal to 1, and as eta goes to infinity, you have f prime goes to 0 and t star goes to 0, tends to 0. Okay. So that's the model equation, and so one can find numerical solutions for this. There is no analytical way to solve this equation. So one has to find this solution use the numerical methods to solve these equations, and so the numerical solution would look something like this. So the numerical solution of for the temperature profile, T star going from 0 to 1, and this is eta. Okay. So the solution would look so this is increasing Prandtl number. So when we increase Prandtl number, we will have a faster fall in the temperature profile. Why is that? So let's say this is 0.01, PR equal to let's say 1000. What happens when we increase Prandtl number? What is Prandtl number? It's nu by alpha, right? Okay. So what happens when we increase Prandtl number? Momentum boundary layer is more important. This is a ratio of delta over, okay, good, delta over delta t. Okay, so this is, rather I should say delta over delta t is approximately scales as Prandtl number to the power of n, right? So when Prandtl number is very large, the thermal boundary layer thickness is very small. So remember, look at your scaling variable eta. Eta is y by x into Grashof number by 4 to the power of 1 by. So when boundary layer thickness is very small, so obviously eta is very small, so all the temperature profile has to be captured at a very small value of eta. Okay. So that's the reason why it falls very quickly for a large Prandtl number. Heat transport coefficient is defined as minus Kf, which is the conductivity of the fluid, into dt by dy at y equal to 0 divided by Ts minus T infinity. So that's the definition of heat transport coefficient. And so from using this expression, using this definition, we can define the local Nusselt number f, that will be x by kf into minus dy divided by Ts minus T. And so, in terms of the dimensionless quantities, this will turn out to be Grashof number by 4 to the power of 1 by 4 dt star by d eta, eta equal to 0. And that turns out that it is a function of Prandtl number, and so that will be 0.75 into Prandtl to the power of half divided by 0.609 plus 1.221 Prandtl number to the power of half plus 1.238 Prandtl number to the power of half. I don't expect you to remember any of these expressions, but it's just important to realize that these expressions do exist. Okay, so it is required; it will always be given to you in your exam. So the local Grashof number is simply defined as g beta Ts minus T infinity into x cube by mu square. So it's simply the same expression that we had before multiplied by the Reynolds number square. So we get x cube by mu square, which is the local Grashof number. Okay, this is the local Grashof number. So the next exercise is to find out the average. So we had two objectives. One is we find the local heat transport coefficient. We want to find the average heat transport coefficient, and that's simply given by 1 by L h into dx. And so that will be 1 by L integral from. So from Nusselt number, we can actually use that expression. We can find out what is the local heat transport coefficient. So that will be Grashof number by 4 to the power of 1 by 4 into GPR into Kf by x into dx. So that's the local heat transport coefficient, and that will be 1 by 4 g times beta Ts minus T infinity by mu square. So all these are not function of x, so we can pull them out. GPR is not a function of x, we can pull them out, pull it out. Kf is not a function of x, that can be pulled out. So there will be integral of to the power of 1 by 4. So that will be x to the power of 3 by 4 divided by x into dx, okay, and that will be Kf by L g beta Ts minus T 4 mu square 1 by 4. What is this integral? 0 to L 4 by 3, come on, it's 4 by 3 into x to the power of 3 by 4, L to the power of 3 by 4. Okay. So this is nothing but integral of x to the power of minus 1 by 4 into dx. So that you integrate, you get a 4 by 3, which comes out because of integration, L to the power of 3 by 4. Okay. So that turns out to be K f by L 4 by 3 into Grashof number based on the length to the power of 1 by 4 multiplied by the function of Prandtl number. Okay. So from here, what we observe is that the average Nusselt number is based on the length should be equal to 4 by 3 times the Nusselt number based on the local Nusselt number based on the length. Okay. So, it is very similar to what we got in the flat plate case, where the average Nusselt number is some function of the or some constant modulo constant of the local Nusselt number itself. So, therefore, we can actually say that the average Nusselt number at any location, which signifies the net amount of heat that is transported till that location in the flat plate, that should be equal to 4 by 3 times the local Nusselt number. So, that is an important observation. So, if I can measure the properties at the exit or at the end of the flat plate, then I should be able to find out what is the local Nusselt number at that location. So, now, all what we have done is basically for laminar conditions, although I should have mentioned it earlier. So, all that has been done so far, all equations and all Nusselt number expressions are for laminar conditions. There is a particular reason why I did not mention laminar. So, remember that there is no reference velocity. So, the question comes in as to how do I define what is laminar and what is turbulent. Okay. So, a new dimensionless quantity called Rayleigh number is actually used for distinguishing the laminar and turbulent conditions for these kinds of problems. So, we define Rayleigh number based on the length, which is the product of Grashof number based on the length multiplied by Prandtl number, okay, and that is given by G beta S minus T infinity into x cube by alpha into nu. So, remember Prandtl number is nu by alpha. So, I multiply it by Grashof number. So, the square cancels off and you get an alpha here. So, the turbulent and laminar transition is actually defined by what is called the critical Rayleigh number. So, if the critical Rayleigh number exceeds 10 power 9, then the flow conditions inside the boundary layer. Okay, remember that it is the flow condition inside the boundary layer, the fluid outside is still at rest. It is a quiescent medium, it is at rest. So, if the critical Rayleigh number, Rayleigh R-A-Y-L-E-I, Rayleigh number is greater than 10 power 9, then it is considered to be turbulent condition. This is something which is very rare and would never encounter a turbulent condition. In fact, the people had not looked at this problem. It is still an open question as to how heat transport would occur under turbulent conditions, free convection. So, there is people have not done experiments. So, there is really no correlation and no analytical expression to find out what is the heat transport in these conditions. So, it is not something that has been studied. So, it is still an open question. Okay. So, it is an open problem. It's an open problem. So, when would Rayleigh number become very large? So, look at this expression. Gravity is fixed. There is a fixed bound for compressibility factor. The temperature gradient is also fairly fixed. It is not that you can have a significant temperature gradient. Length scale is also fairly. So, it is the viscosity and diffusivity which actually tells you when the Rayleigh number is going to be significantly large. So, it is very difficult to encounter a situation where the fluid's viscosity and the thermal diffusivity is in such a way that the Rayleigh number is significantly large, which is about 10 power 9. So, that is not something that has been encountered, but maybe there is a situation, we do not know that. Alright, so we will switch to another geometry for free convection. With that we will finish today's lecture. So, this is natural convection around cylinders. So, the analysis and the boundary layer formation is very similar to what we actually discussed in the external flows case, where we have a long cylinder. We have a long cylinder which is actually going inside and outside the board, and so that let us say that this cylinder is suddenly dropped inside a quiescent fluid, and now you will have a boundary layer which is formed around it. So, this is maintained at a certain temperature Ts, okay, and let us say this is angle theta. So, one can work out what are the correlations for the Nusselt number. So, suppose if the cylinder is maintained under isothermal conditions, let us say we know how to maintain the temperature of the cylinder. So, the Nusselt number based on the diameter is given by 0.6, 0.387. This is empirical correlation, remember that. Okay. Rayleigh number to the power of 1 by 6, 1 plus 0.559 divided by Prandtl number power of 9 by 16, power of 8 by 27, and the square of it. So, all these funny numbers you can see immediately tells you that it is some sort of correlation, is not completely analytical. Okay. So, this is a general correlation for these kinds of problems, and there is also an alternative correlation which is given by some c times to the power of n, and there is a table which sort of tells you what are these constants for various values of Rayleigh number. So, that will be 10 power minus 10 minus 2, 0.675 and 0.058 and 10 power minus 2 to 10 square, that's 100, 1.02 and 0.148. Okay. So, that is the Rayleigh number, that is the constancy and n for different ranges of Rayleigh number. So, similar to what we saw in the cylinders, so the Nusselt number versus theta. Okay. Remember, we saw that the Nusselt number increases and then it suddenly falls, and in a similar fashion you would expect that the Nusselt number would actually between 0 and pi it simply falls. What is the reason for this fall? Remember your cylinder with external flows, what is the reason? There is going to be a separation point, right? So, when this fluid is flowing around, the fluid is now no more in contact with the surface, and so you expect that the Nusselt number that you would calculate using these correlations would actually fall as you go close to the other end of the cylinder. Remember that theta 0 to pi actually goes from, this is 0 and pi is here. Okay. So, that is the kind of profile for Nusselt number that you would expect, and once again I do not expect you to remember these expressions, and in fact you would not be expected to remember these expressions even in future when you actually have to use these expressions in real systems. So, these expressions are always cataloged in several books and it is always available to you, but it is important to know and realize how to use these expressions and what is the value behind it. So, what we will see in the next lecture is we will start a new topic. So, we will look at some sort of an application. So far we never looked at phase change. We never looked at phase change. So, we always assume that the fluid which is flowing is always in the same phase. Okay. So, what we are going to see next in the next classes, we are going to start discussion on boiling. What happens to a system when there is phase change of the fluid, that is, it goes from liquid to the vapor state, and a few lectures down the line we are going to see the reverse, what happens when there is condensation. So, these two, they play an important role from industry point of view, because there is always steam which is flowing in different locations, in different pipelines in a process industry. And so you will always see that at some location a fluid is being boiled because of heat transport, and in some location the heat that is carried by the steam is actually transported to another fluid through a heat exchanger, where the steam is actually condensing. So the nature of the heat that is actually left or taken up by the fluid is the latent heat. So we are going to start looking at when there is latent heat which is actually playing an important role in the transport processes, how do these analyses change, and what's the nature of these correlations that we're going to get, and what's the nature of solutions that we're going to get. Okay. So that's what we're going to start in the next lecture.